is chapter 1, and in this video clip we will discuss very important and fundamental concept of the solid mechanics, which is normal stress and strain. Okay, so I already told you guys the symbol of the stress is this, and we call this as sigma, right? And the equation of the stress, the sigma, is equal to P over A. In this case, the P represent normal force and the A represent unit area. So overall, the intensity of a normal force per unit area is termed the normal stress, and it is expressed in units of force per unit area, which means Newton per meter square. And also we can use other SI unit as a Pascal, and we can identify that 1 megapascal is equal to 1 Newton per millimeter square. Okay. Right, so here, as you can see, if the force is applied to the ends of the bar, right, ends of the bar forces, such that the bar is in tension, then tensile stresses are set up in the bar structure. So we can cut one side of this bar structure, then the stress acts in the direction perpendicular to the cut surface. So this is cut surface, right? It is referred as normal stress. Another type of stress is called shear stress. So here we can define that when the bar is stretched, the resulting stresses are tensile stress, and we used positive sign convention. And if the bar is compressed, the stress are compressive stress, and we used minus sign convention. So two different stress, tensile stress and compressive stress, and correspond to the tensile loading condition and compressive loading condition. Right? Then using this concept, we can solve one example. So here you can see the two prismatic bars, right? These are two prismatic bars are rigidly fastened together and support a vertical load of 45 kilonewton here, right? Vertical load 45 kilonewton. In this case, the upper bar is still upper bar. This is upper bar, right? This is upper bar. This is still, right? Having length 10 meter and cross-sectional area 60 centimeters square. The lower bar, this is lower bar is rest, right? having length 6 meter and cross-sectional area 50 centimeters squared. And here you can find the elastic modulus of both steel and brass. For steel, elastic modulus is 200 gigapascal and brass is 100 gigapascal. In this case, we have to determine the maximum stress in each material. So by using the fundamental determination of normal stress, which means sigma is equal to P over A, we can solve this problem. Okay, so let's continue to solve this problem. Okay, the maximum stress in the brass bar occurs just below the junction at the section BB, right? This section BB. So, therefore, the vertical normal stress is caused by the combined effect of the load of 45 kilonewton external force loading condition together with the weight of the entire brass bar below BB, right? This section. So, we have to find the specific weight of the brass bar. So using this table here, brass, right? And the specific weight 0.307 and in the pound per inch cubic. And using the SI unit, we can use this one, 84 kilonewton per meter cubic. Then back to the original page, the weight of brass is calculated 6 times 50, 10 to the minus 4 times 84,000, and this should be 2,520 Newton. So again, back to the table, we can use this value using this specific value in table, right? Then now we can use the fundamental equation of the stress, sigma brass actually is equal to P over A, and we already know that the external force here, one more time, 45,000 plus what else we have to add? The weight of the entire brass bar, right? So that is, we already calculated here, right? 2,520 Newton. And the cross-section area, actually the cross-section area is given here, right? So 50 times 10 to the minus 4. Eventually, the stress in brass is 9.5 megapascal. And about the steel, right? The maximum stress in the steel bar. Actually, we can follow the solution process. Again, the maximum stress in the steel bar occurs at the section AA. This one, section AA, right? The point of suspension, because the entire weight of the steel and brass bar gives rise to normal stresses. So we have to consider the entire weight of steel and brass, right? So the weight of the steel bar here, one more time, we have to use the table. Here is the steel, and we use the SI unit, 77 kilonewton per meter cubic. So weight of steel can be calculated 10 times 60, 10 to the minus 4 times 77,000. That is 4,620 Newton. So eventually the stress of the steel is equal to same thing, right? We use the same, the equation P over A, but the specific, the force to identify the stress, normal stress of steel is different in comparison with the stress of the breath. So first, we have to consider one more time, this one, external loading condition plus what else? We have to consider both steel and brass weight, right? So we already know brass weight is 2,520 and we just defined that the steel weight is 4,620 Newton. And overall the section steel, the cross-section area is already given, right? 60 times 10 to the minus 4. So eventually we can obtain this value as your normal stress of the steel bar. So using the basic equation of stress, sigma is equal to P over A, we can solve this kind of problem. Okay, then let's move on to the next concept, which is the normal strain. So here, let us suppose that the above figure has tensile forces gradually applied to the ends, like this, right? Gradually applied to the ends. The elongation per unit length, which is termed normal strain and denoted by, may be found by dividing the total elongation delta by the length L. So here, this is the initial length, and this is the deformation, which means the elongated deformation by the tensile loading forces. So, using this geometric condition and external loading force condition, we can define the strain. So here you can find the symbol of the strain, epsilon, right? We call this epsilon, and the epsilon, which means the normal strain can be identified. Epsilon is equal to delta over L. Right, so normal strain is kind of some dimensionless the property. So the unit is none, which means that this is dimensionless identity, physical identity. Okay, so the requirement for normal strain and strain, we have to consider this basic assumption. The bar should be prismatic and the load acts through the centroid of the cross-section, and the material should be homogeneous. So this is kind of some fundamental assumption to define normal strain and normal stress and normal strain by considering the bar structure. Okay, then let's move on to next page 4, solving the strain-related problem. So here you can find specific figure, right? When the bungee jumper, this is bungee jump structure, and when the bungee jumper in figure 1 stands on the jump platform, the unstretched length, which means initial length of bungee cord, is 12 meters. Right? This should be initial length. So we can use this specific geometric condition to define the strain, right? Assuming that the bungee cord is stretched, now the bungee cord stretches uniformly along its length, then determine the extensional strain in the bungee cord when the jumper hits bottom, very bottom, where the extended length of the cord is 37.1 meters. So this is what? This is deformed length. And we can highlight this as star. So using the fundamental strain equation. Epsilon is equal to what? Delta over L, right? We just defined it. And in this case, we can define the delta, the total, which means that the deformed lengths indicate the total length of deformed structure. But to define the strain, we have to use the exact deformation value, which means delta. So the delta can be defined L star minus L, which means deformed length minus initial length over L. And we know that deformed length is what? 37.1, and initial length is 12 meter. And it's divided by its original initial length 12. Then we can identify that is 2.09. And again, this strain is kind of some dimensionless, unitless property. We can find that the overall the unit can be deleted like this. So this should be again dimension less physical identity, right? So this is very simple, but we can remind the basic concept of strain through this specific example. Okay, then let's move on to the next concept of uniaxial stress and strain. Okay, so uniaxial stress strain is kind of similar concept of normal stress and strain, but the different thing is that mathematically we can define the stress and strain, the concept of stress and strain, right? As you can see this figure, okay? For prismatic bar, the rods extrude the centroid of the cross section. So this is the here. This is the cross section area, right? So this entire. Again, the rods extrude the centroid of the cross sections, and the material should be homogeneous. The resulting state of stress strain is called uniaxial stress and strain. So using the fundamental assumption, rods extrude the centroid of the cross section and the material be homogeneous, then the resulting state of stress strain is called uniaxial stress and strain. And here in this graph, we need to consider a prismatic bar of arbitrarily cross-sectional shape subjected to axial forces P that produce uniformly distributed stresses. So we can consider this specific element of area. Then by reference to this element of area, we can define this whole cross-sectional area. So again, we need to consider this prismatic bar of arbitrary cross-section shape subjected to by the axial forces P that produce uniformly distributed stresses. So to define this specific cross-section area, we always have to consider the fundamental, which means the finite element of this cross-section area. Okay, the moments of the force P can be defined like this, right? We know that using the perpendicularly applied loading condition, multiplies by the momentum, we can identify the specific moment, right? So the mx, two different moments of the force P can be identified. In this case, P y bar minus P x bar, something like that. So in this case, we can define that the differential force acting on an element of area, which means that we can use this specific relation. dA can be identified as sigma dA, the differential force acting on an element of area, dA is equal to sigma dA. So using this specific condition and the moments of the force, the defined moments of the force defined by the force P, the total moments are obtained by integrating, right? Integrating over the cross-sectional area. So here, two different equation can be identified. So basically, sigma is uniformly distributed, right? So we can rewrite the moment equation like this: Py bar, which means the mx is equal to sigma integration y dA, because again the stress is uniformly distributed, right? So we can put the sigma in front of the integration symbol, same as this, right? Px by the sigma integration x dA. And then using this specific condition, we can define that by dividing it, that y bar can be identified eventually, integration y dA over A. And in this case, we can identify that sigma is what? P over A. This means we can define A is equal to P over sigma. Okay? And x bar is eventually equal to integration x dA over A. Okay? So this is very important concept to further define the basic and the critical concept of overall stress and strain. So uniaxial stress and strain is now actually we defined it, and another type of stress strain can be defined by this kind of the concept and mathematical protocol, something like that. Okay, then I would like to stop here, and we'll continue the mechanical properties of material in next video clip. Okay.